Hi, everyone. Welcome to what will probably be the final AI Edge seminar of the AI Edge seminar series in autumn. It's a great pleasure to have one of our own return to the Ohio State University, Professor Yin Sun. Professor Yun Sun got his PhD from Tsinghua University in China several years ago. And then he was a postdoctoral researcher at Ohio State for a few years before he joined Auburn University, where he is an assistant professor. Professor Sun is probably one of the best known researchers in the area of age of information. He has written seminal papers in this area, including a recent book on this topic, and it's a real pleasure to have him talk about how data freshness affects real-time supervised learning. Go ahead, Ian.
Okay. Thank you very much for everyone to spend your time to come to my talk, and it's my great pleasure to come back to Ohio State to reconnect with old friends and also these new students. So this conference room is a room that I'm really familiar with. So my office, old office is just next door. That office for postdocs. For productivity, that office doesn't have a window. So it really helps us. So, and when I have some issues, there's something that I cannot prove, I usually come to this conference room around midnight time. There's nobody here, and I will actually have a soccer. I will just go around this table round by round, and then that helps me to get some my proof ideas. But I can guarantee to you that those appearance of damages is not written by me. Yeah. So then today I will be talking about how data freshness affects the real-time supervised learning and how to design communication system to improve the learning performance. So this is a joint work with my PhD student, Cameron Shisher. So he is a 5th year PhD student, and this talk contains about 2 years of his work. We start from the scratch, and we don't really use any prior work. So he just started all by himself. So in this talk, I see. So this is the outline of my talk. I will be first talking about real-time supervised learning and its applications for network intelligence system. And then I will introduce its metrics for data freshness, which is called age information. And then the technical part will contain 2 questions. The first question would be, how does data freshness affect the real-time supervised learning? And we actually find some counterintuitive phenomena from experiments. It's actually says that fresher data is not always better. So that is different from people's general belief in this area. And to understand this counterintuitive phenomenon, we actually have developed information-theoretic analysis and accompanied with some experimental studies. And then I shifted to design of communication system. I asked this question: how can we design communication system to improve the performance learning? And for that, we designed some scheduling algorithms to minimize inference error. And at the end of the talk, I will discuss some future directions. So real-time supervised learning is crucial for many network intelligence systems. For example, in vehicle networks, a vehicle needed to predict the trajectory of nearby cars to avoid collision. And in remote surgery, the doctor needs to know the movement of a surgical robot, which could be operating on the patient at a really remote, far away distance. And there exists a lot of applications related to this, including UAV navigation, factory automation, AR and VR, some kind of real-time surveillance scenarios, analytics of the video data. So then if we look at this example, so suppose that we have a camera that is collecting this video data and sending this video, short piece of video from the transmitters through a network to a receiver side. And here we will use XT to represent a short video that contains U subsequent video frames. And then at the receiver side, the neural network will use the received new short video to predict the current video frame. So at time t, because of the communication delay over the network, the freshest received video is not necessarily like the video generated at time t. It could be a video that's generated at an earlier time, and there's a time difference delta t. So I will call this a short video xt minus delta t as the feature, so which is a term usually used in machine learning. And the target, the current video frame we're trying to predicting, that is the labor. And then the time difference, delta t, represents the staleness of the feature data for predicting the current labor. And this delta t is actually the age information that the people are really referring to in this age information area. So yes, I need to. Okay, so this is a slide that provide a clear definition for the age information. So at any time t, the age information is defined as a time difference between the current time and the generation time of the freshest received packet. So let's look at time t. Okay, so packet I is assumed to be generated at time si, is delivered at time di. So di is before time t, which means at time t, this packet has already been delivered. And there are a number of packets. So among all these packets that has been delivered, si is the most recent time, which means it is the freshest packet. So then the age of information at time t is simply the time difference between time si and time t. Okay, and then as time goes on, the age will grow linearly over time until a new packet, a fresher packet, is delivered to the receiver, and then the age will drop to be determined by the new packet, and then it will grow again. So that is the pattern of changes of the age as a function of time. Here I also illustrated the delay of a packet, which is from the generation time to the delivery time. So you can see delay is a function of a packet, the age is a function of time. So there's some difference. And furthermore, if you try to further understand about the difference, we can look at this example. So if we have this communication system where the arrival rate at the transmitter side is really low, in that scenario that the queue is almost empty. So just think about, okay, you're trying to buy a coffee at Starbucks. Okay, so the queue is empty, and then the delay is pretty low. It's just about equal to the service time. And but however, when you look at the age, it's actually pretty high. The reason is that the receiver is updated very infrequently. So, you get an update and then you wait for a very long time for a second update. So you are trying to speculate what is happening at the transmitter side. So because of that, for this scenario, the age is actually quite high. On the other hand, if we have a very high arrival rate, in that scenario, so your buffer is full, and that means the queuing delay will be very long. So delay is very long. And when a packet is waiting in the queue, it's actually becoming stale. And because of that, the age will be also very high. So then you can see that age is a curve that first decays with the arrival rate and then increase with the arrival rate. But the delay is just a monotonic increasing function with delay. So that's the starting point. People realize, okay, these two concepts are pretty different from each other. Now, with the concept of age of information to be established, then we can have two different setups for machine learning. So one of the scenarios that, okay, you provide both the feature and the age to the network, that is called age-aware learning. There's another scenario that is age-agnostic learning, where you only send the feature to a neural network. Okay, now suppose that this age dynamic, the communication channel is unreliable, the communication delay is random. In that scenario, you can actually see that age-aware learning can achieve much better performance than age-agnostic learning for one experimental result that we have. So that actually suggests that, okay, age of information would be pretty important for these kind of machine learning settings. And then the follow-up studies of this talk will be focusing on age-aware learning. So that is the general setup. Now we move on the first part. How does the data freshness affects learning performance? So we first consider several experiments. So this is an experiment of a video prediction. We adopted the algorithm, and the data set is provided by a research group from UC Berkeley. And we run their video prediction algorithm, and here's the results. So you can see that the training error and inference error, they're both growing with the age. And that means fresher data will be better. So because fresher data will lead to a smaller inference error. So in this case, in the second experiment, we consider a leader-follower robotic system, and the leader robot is sending a state, which is actually it's a joint angle at a particular time to the follower's robot through a communication channel. And this channel has a constant transmission time. Then the follower robot, once it received this recent state of the leader's robot, they will move just trying to get close to this indicator of this good location, move towards that. So, and here is the simulation. Let me see that. How you just play this. Yeah. Okay. So basically, this is the simulation environment for this. So the leader robot is moving, but have no actual object. But the follower robot is actually just the leader robot probably does demonstration about how to moving this can without hitting the table. And the follower robot here would actually trying to mimic the leader robot's movement. So this is simulation we consider, and then we actually would ask the following question. So the leader robot also need to know how the follower robot movement is like. So suppose that, okay, it's really at the communication distance is pretty long, that feedback channel takes time, and you wanted to understand, okay, what's happening at the follower robot side. And in that case, you can actually add some kind of estimator, or add this, in this case, a neural network to predict the state of the follower robot. And then we run this kind of supervised learning algorithm by using the training data collected from our simulation. So here's the results. You actually see that the training error first decrease with the age and then increase with the age. And that means a stale feature is actually better than fresh feature in this example. And that is the thing that we observe as a counterintuitive phenomenon. And I will explain why this is true in a few slides. So we also have a number of additional experiments. And so, when my students show me this, we just cannot really always believe this. We just continue to run different kind of simulations, experiments to see what's happening. So this contains temperature prediction, solar power prediction, and the prediction of the channel state information in wireless communications. So then you can see that, okay, these a lot of these curves are non-monotonic. So for temperature prediction, we actually could guess what is the reason. So suppose that we're trying to understand the temperature at the current time, and then the data that is 24 hours ago at noon yesterday, that will be more relevant to the temperature now in comparison to the temperature that you collected at midnight yesterday. So
this has to do with the non-stationarity.
That is true. System, right? Non-stationarity, but it's actually theoretical pattern, some kind of so basically what we are trying to say is that what is happening here depends on your data. So if we don't really have any restriction on the data, then what the data shows to you needed to just accept that. So that's the observation that we have. So we actually find that, okay, inference error is function of the AOI, but the function may not be monotonic. And then we're trying to interpret why this is true. So we consider a class of very popular supervised learning algorithm, which is called empirical risk minimization. And there exists a loss function L, where A here represents an action. So I provide two examples here. So suppose that we are using neural network for estimation. In that case, this action would be my estimate y hat. And then this loss function is just a quadratic function that, okay, you have been using for your, estimation calls. And, in another case for softmax regression, so basically that is a different term for maximum likelihood estimation. So then in that scenario, the action that you are providing is actually a distribution. And the loss function here is actually a minus log likelihood. Okay, so then what the neural network does is that the neural network will take in the feature and the AOI as input and provide this action as output. And this set lambda is a set of all functions that can be constructed by the neural network. Okay. And this is also we have a distribution represented in macro distribution of the training data. Now, the issue is that if we want to understand how this training error varies with the age value delta, the problem is that this set lambda is very complicated. And because of that, trying to do some analysis will be very challenging. And then we actually.
So Yin, just to make things very simple, okay.
Yeah.
I'm going to give an example, okay, where I think your point can be made very clearly. Let's say that your learning is being used to predict channel. Okay.
Right.
And let's say that you essentially have a periodic channel.
Right.
Which basically flips from 1 to 0.
Yes.
In every other time slot.
Yes.
Okay?
Yes.
In that case, it's clear that 2 time slots earlier will be a much better predictor of the current channel than 1 time slot.
Definitely.
And that has a larger age.
That's true. That's true. Exactly. That's
the key, I think, idea.
Right? The key idea and making things very, very clear and simple. So then what happens is that we try to analyze, okay, this function as a function of the age. And we find that it's convenient to consider an information-theoretical bound of this training error, where to get this bound, we actually replace the set lambda by this another set of phi. And this set phi is a set of all possible functions, mappings from input to output. And now because this set lambda is smaller than the set phi, naturally we will find that this will give you a lower bound of your training error. And then this is actually has a term has information theoretical meaning. It's a generalized conditional entropy associated for the loss function L that we choose. So if you choose different L, then this entropy will change. And for convenience, in our paper, we just call it L conditional entropy, representing this loss function L. Now, if the neural network is sufficiently wide, sufficiently deep, and if the training algorithm really works well to achieve this optimal point, then these two sets of functions will be very close to each other. Then you could say that, okay, I can just utilize this conditional entropy to represent as a very nice approximation of the training error. Okay. We also look at the inference error, and the inference error can be similarly approximated as something that is a conditional cross entropy. So I call it L conditional cross entropy. Now, if the distribution of the training data and the distribution of the inference data, they are close to each other, then I can also approximate this conditional cross entropy as a conditional entropy. So then basically, just for the sake of our understanding, we can now focus on some kind of this conditional entropy term. Okay. Then there is some tools from traditional studies on statistical learning. So that is the data processing inequality, and I'm sure that everyone, all the students here have learned about data processing inequality from information theory. That is for Gaussian entropy. Okay, now we're talking about potentially non-Gaussian entropy here. But then we can actually show that if the training data and the inference data forms a Markov chain, then this conditional entropy is an increasing function of the AOI. which is pretty nice for us. And now what we have is that in practice, some of the scenarios it is monotonic, some of the scenarios non-monotonic, and it actually give us indicators because the distribution of the data. Is that periodical? Is that Markovian? Or is that non-Markovian? So we need to understand about that part. So then we propose a relaxation of Markov chain. Okay, so we introduce this thing called the epsilon Markov chain, where we utilize some chi-square form of conditional mutual information, and I let it to be smaller than epsilon square. And if that is happening, then I call it to be epsilon Markov chain. And when epsilon is equal to 0, then it reduces to the traditional Markov chain. Okay, and then we worked out to generalize data processing inequality for Markov chain to something called epsilon data processing inequality for epsilon Markov chain. So we can actually show that this conditional entropy contains two terms. The first term is an increasing function with age. And the second term is big O epsilon. So that means, okay, if epsilon is small, then you are getting this term to be very close to an increasing function. When epsilon is larger, then you are deviating from an increasing function. Okay, so then basically that is what we find, and we can actually see that, okay, the first case could be similar to a Markov chain. The reason is that each time the video only change a very, very small bit. So therefore, a sequence of video can be really approximated as a Markov chain. And now for the second case and for the third case, you can think about it. It's quite different from a Markov chain. So when it is close to Markov chain, then you have a function that's increasing with the age. When it's far away from Markov chain, then the function could be non-monotonic. Okay, that's a general theory. And then we further look at this special case. Okay, we have this counterintuitive phenomenon. Why there is some scenario where stale data could be better than fresh data? So we could actually still interpret this. So the idea is that we actually utilize a tau example. So this tau, in this tau example, I assume xt, the feature to be a Markov chain, and the label yt is a function f of xt minus d. Okay. So then you can view this xt as an input of a causal system, and the output would be yt, and the system has a delay d, and the system could be nonlinear by this function f. Okay, and then if you consider a Markov chain graph of these variables, you can see that from yt to xt minus d towards the future, that is one Markov chain, okay? And then yt to xt minus d towards the past, that is another Markov chain. By using data processing inequality on these two Markov chains, then you can prove that this conditional entropy decreases with the age when the age is small, and increase with the age when the age is large. So that is a behavior that is just the same, pretty similar to this our experimental results. So what is happening is that if we are utilizing the system input to predict system output, you will see this. So in other words, if we are trying to predict the reaction, if your system is moving and you are trying to predict the reaction of nearby systems, then you will see that, okay, this inference error will have a low point when, for stale data is actually better. So that is what we observed and interpreted, and that is summarized, allow me to summarize the first part. So we studied how the age affects the learning performance, and we find that fresher data is not always better. And to understand this, we provided experimental results, we provide information-theoretical studies. So that's the first part. In the second part, then I will look at how to design communication systems to improve learning performance for these pretty real-time system. So now, because of fresh data may not be the best piece of data, so I wanted to have a transmitter that will have both fresh data and old data, and the scheduler will be able to choose which data to send. And I propose this model that is called the selection from buffer. So there's a buffer that keeps B most recent features. So the feature that is fresh, that is xt, the feature that is a little bit earlier, that is xt minus some value. And this buffer size is B, is a constant. And for the scheduling policy, I will decide when I should send out a feature packet to the receiver, and also which feature I should choose to send from my buffer. Okay, so the packet transmission time is basically modeled as a queuing server. The service time is IID. The distribution could be pretty general. Then this model basically allows us to send earlier features, and it's also fit with these hardware design pretty well. So because a lot of hardware are just providing you a sequence of these packets, and then you just keep a buffer and then you can run this. Implementation should be easy. In our earlier studies, there is some model called the generated at view model. That's a special case of this one. So that's a scenario where the buffer size is only equal to 1. Okay, so we do some extension over this earlier work. Our goal is to minimize the time average inference error. Okay, and this function P is the inference error at a particular time T. Okay, and I want to note that even for the first part of the study, we considered information-theoretic approximation. However, in the second part, I just realized that, okay, the function we are optimizing is a general arbitrary function of the age. Okay, then I don't really have to rely on information-theoretical approximation. Let's just optimize the actual inference error, whatever the function is. Okay, so then we try to solve this problem, and we try to make 2 decisions: when to send, which packet to send, and the scheduling policy would be containing all kind of causal scheduling policies. And the question would be, okay, which scheduling policy would be the best policy, and what kind of insight can we find from the optimal solution? So that is what I'm trying to do. The problem is not very easy. So in earlier studies in the area, people has been considering increasing AI functions, and now we are trying to optimize potentially non-monotonic AI functions. So that will give us some theoretical challenge that we need to address. And okay, so now we provide a solution. So first of all, we look at the sub-problem. For this sub-problem, I will fix the position of the packet we are choosing from the buffer, always from the B's position, and then decide when to send it out. Okay, so that's a sub-problem. And this theorem tells us, okay, the optimal solution for this sub-problem should be that it send out the next feature packet. Well, first of all, you need the channel to be idle. Okay, that's fine. Idle channel, that's fine. And also the second condition says that, okay, there exists some term which is called the Gittins index, and this index should be exceeding a threshold beta. Okay, and then what is this threshold? This threshold turned out to be a unique root of the following equation. And this equation has a unique root. You can utilize bisection search to quickly find this unique root. And for the terms, beta is the whatever we are trying to, the root we are trying to solve. Di is the delivery time of the ith feature, and p is just this general function of the age. Okay, and then that is give us a way to compute this threshold beta. Furthermore, beta is exactly the optimal object value of this subproblem. Okay, so basically, okay, you take the threshold, and threshold is the long-term average. Okay. Now, this theorem is actually pretty general. First of all, it holds for pretty general AOI functions, not necessarily a linear function, not necessarily a monotonic function. Okay, and also the transmission time distribution we consider here is also very general. The only requirement is that all of these expectations here must be finite. We just only need that. Okay, so that gives us a solution for this subproblem. And next, I will talk a little bit about this Gittins index function. So it took us some time to realize that, okay, Gittins index and the AOI minimization is actually related to each other. So we consider this AOI bandit process. So the age grows by 1 in each time slot. And for each time slot, it receives a reward, R minus the penalty function P delta T. And R is a constant. So then the bandit process has 2 actions, whether to continue or it to stop. So if you choose to stop, now because I have this random transition time, you try to stop it, but it takes a little bit of time, random time Ti to stop. And the goal is to determine when I should stop. So that is the optimal stopping problem. So by solving this optimal stopping problem, we can find this Gittins index is actually defined as a value of the reward for which both the continuous and the stop actions, they are equally profitable at a given state delta. So then basically this is optimal stopping problem is the way you compute the Gittins index in multi-mandate literature. So we can write this Gittins index in this standard form where you are trying to optimize this optimal stopping time nu, okay? And then this is something, okay, you can compute it by using like a square type of complexity. It's a polynomial type of complexity, but we actually find that because our problems still have some further structure, we can simplify this optimization problem from an optimal stopping problem to some kind of integer optimization problem with no randomness, just one dimension in this variable tau. And after that, this becomes very easy to evaluate. Now,
how large is tau here?
Tau is any kind of integer. So mathematically, it's like that. For evaluation, then you put a bound. Yeah. So basically, until that age is too high and the inference error is no longer changed. So when age is very high, whatever data you have is becoming irrelevant to the actual scenario. So that's the case that tell you what would be an upper bound for this tau. Okay. So this is basically the best possible analytical result we can get. You always see this expectation, and this expectation is always about your random transmission time.
So here you're taking a running average of the expectation, right, in your final equation?
Yes.
Right. So you're taking a running average of the expectation. So basically the idea is that the hope is that eventually things will start being below the running average, and
right,
you can kind of cut it off.
That's right. So somehow there is in the future there could be an age value that the inference error becomes low again, and then you have to consider all that kind of future opportunities. So when you are deciding, okay, do I want to send now? Do you want to send to later to enjoy that benefit? So then we come back to the solution of the overall problem, making both decisions. It says that you look at the optimal solution of these sub-problems and just choose the packet which give you the minimum among all these sub-problems. And then, once you decide which packet to send, then, you just send the feature when 2 conditions are satisfied, or where the channel is idle and the Gittins index is exceeding a threshold. And this threshold now becomes the optimal object value of this overall problem. Okay. So there is some novelty in this piece of work. First of all, this selection from buffer model is new. It doesn't really exist in earlier studies, and we find this optimal scheduling policy for minimizing pretty general AI functions, and it has some insights we can exploit. Okay, so this gives us the solution for the general case, and then in the special case, suppose that this function of the age is actually increasing. Okay, if it is actually increasing, then fresher that is better, then we can actually find that this Gittins index can be reduced to this much simpler expectation. And also it says that, sending from the position B star equal to 0 is the best. So you should always send a fresh packet. So as in the traditional generated at view model. So it means that, okay, in that case, the early studies is indeed the best. So previously we have this expectation in our paper, and then we don't know what that means. Now we know that it's a special case of this Gittins index. Okay. So then this is our simulation performance. So comparing to periodical updating, we can reduce the inference error by about 8 times. And comparing to the previous generated at view model with optimal scheduling policy, we can potentially achieve 3 times of performance gain for reducing the inference error.
So is it because of 2 reasons? Is it because the generated will, as you showed in your original paper, is also this is generated with optimal scheduling.
Which optimal scheduling?
Oh, okay, I see.
Yeah.
I see. So with 0 weight, there is substantial gain.
Yes, that is the green one.
Okay.
Yeah.
So that means there is some larger variability, right? Like you showed, because the 0 weight must be suboptimal for that.
Right. So we consider this kind of a reaction type of
I see.
feeding that data to this generated this simulation.
Cool.
Okay, so then we have an extension to the multiple source scenario. Suppose that we have a number of sources and we're sending these feature data to different neural networks, and they are in one cellular system. The cellular system could have a number of channels, or in one Wi-Fi system. So then each of the sources could have a different inference error function. Their transmission time could be long, could be short. So there will be a lot of dynamics over the sources, and the channel, there are at most there are n channels, so you can serve at most n sources at the same time. The scheduler needed to determine which source to send, which feature from the buffer to send. Okay, and it even allows all the sources to be silent, okay, if they figure out that being silent is better. Okay, so we are trying to minimize this weighted time average inference error, and this is a multi-banded problem with multiple actions. So in general, it's pretty challenging, and we resort to Whittle's index. So we can prove that, okay, the resonance banded problem we are considering here is indexable, and the Whittle's index has pretty complicated expression, and this Whittle's index can be expressed by using the Gittins index we obtained in the single user part. So only after we obtain this Gittins index, we were then able to express this Whittle's index in some kind of analytical form. Okay, and then for the policy, then you just send the features with the highest Whittle's index over the channels that are idle, and you need this Whittle's index to be positive. If the Whittle's index is negative, then you just remain silent and not really using that channel. So that's is the scenarios where in some of these earlier studies, waiting is better than sending. So I did not explain that too much, but it's happening here. So I would say that after we submitted this paper to Mobihawk, and we went to the conference, and then a colleague, Professor Yihong Ho from Texas A&M, he suggested us, oh, this is the thing that you have, and I think there's something that you need to further improve. So the reason is that we actually have this problem with multiple actions. So the decision is not only about which source to send, but also about which packet you should pick from the source you choose to send. So it has a 2-layer decision problem. So theorem I'm showing here give us the answer of the first question. However, when you're choosing which packet you should send, you actually need to have this weight lambda as a dual variable that should be tracked over time. And then, there will be some additional operations to find which packet you should send. So the packet that gives you the highest Gittins index, it may not be the best packet to send over there. So that is something like, I could not really get that kind of intuition from my own thought, but, it will help me with that. And then we needed to further refine this to understand about something more general in terms of indexability with multiple actions. So then this is a summary of my talk. In the second part, I consider the communication system design for machine learning. We propose this new model that is a selection from buffer model. And I think that is also more natural for hardware design. And then we develop the scheduling policies to minimize inference error. So basically, we need to determine when to send and which packet in the buffer to send. So in the single source scenario, we find the Gittins index is very useful for us. For the multiple source scenario, we were able to show that, okay, Whittle's index can be expressed in almost closed form expression. And I don't know why.
That's strange.
Right. Let me close this. Is that one? Okay. Now it allows me to show this. So there exists a number of potential future directions because, okay, this is really the first piece of work on this kind of model. So first of all, this packet length U, it actually has an impact on the learning performance. So if U increases, so first of all, from this traditional understanding by channel, the data sequence will be getting closer to a Markov chain as U grows. And when it gets closer to a Markov chain, then you can see that this inference error curve getting closer to an increasing function. That's the first thing. The second thing is that as U increases, it means that you are using more data to infer, and that means that the inference error could be coming lower. So that is the observation we can make. And on the other hand, if you, from a communications perspective, if you send a longer feature, it means that your transmission time will be longer. So then you actually have this kind of trade-off between the inference performance and the communication resource availability. So it's better for us to design this feature length parameter in a good way. And that leads to this inference communication co-design problem to achieve even better performance. And then based on the models used in this area, we could consider different channel models, irregular channel, Markovian channel with two-way delay, and those are the scenarios we do not fully know yet. And then we can also try to generalize this work to the scenario, not only based on the age, but also based on something like the signal value or the feature value that you can utilize that to making decisions. In practice, data distribution is also varying over time. So here we are saying, okay, the inference data distribution is close to the training data distribution. That is, in general, is not true. So there will be some kind of time-varying data distribution problem. And that will lead to these kind of questions for online learning, where I'm pretty sure that we have a lot of very good students here in Ohio State, thinking about that kind of technique. For sources, sometimes you could have 3 cameras which are just traversing to the same building. So that is a correlated source, and that can be considered. And the other thing is that we have been considering these questions like when to send, which packet to send, and in the next stage we could further consider what to send, and that is belonging to this new research topic which is called semantic communication. Yeah. So with that, I think I finished my talk. Thank you very much.
Thank you. So, a very interesting talk, Ian. One question I have is, again, I'm sort of trying to get an intuitive understanding on the first result.
Right.
So for non-stationarity, I think the intuition is very clear.
Mhm.
Right?
Yeah.
Okay, so let's now think about the result from the stationarity point of view. So you have a Markov chain.
Okay. Okay.
So what you're saying is that so is that a sufficient condition? Is that, or is it necessary and sufficient? What I mean by that is that if it is a Markov chain,
Mhm.
then you essentially have this,
Increasing
function.
Yeah. Right. So I mean, if, in the theorem basically says that if it is a non-Markov chain, you have this parameter epsilon,
Mhm.
and this parameter epsilon is saying that it's an additive term on top of increasing function.
Okay.
So the epsilon must be large enough to destroy this increasing pattern. So it's not really
So it's not
necessary.
not
Not
necessary.
necessary.
Okay. That makes sense. But so I guess for the sufficiency part,
Mhm.
is the way to understand it,
Mhm.
if you think of what a Markov chain is,
Mhm.
it basically depends only on the most recent state,
Right.
right? It doesn't depend on the past history.
Right.
Right. And therefore, you would
Yes.
imagine that the freshest information, which is the most recent state,
Right.
is the right one.
Right.
Is that roughly the logic?
That's logic is
Okay.
totally correct.
Okay.
Yes. Yes. Yeah. So I mean, it's more related to our domain. So when we
Right.
consider real-time control, like a robotic networks, you're trying to understand about the reaction of nearby cars, then you really see that, okay, a little bit old information can really be helpful for understanding nearby cars' behavior.
Sure. Okay, cool. Very good. Yeah. Any other questions from the audience?
I have a
Yes, please.
So in your second part, you have you try to solve this problem by first considering a subproblem with the
Right.
first B, right?
Right.
So when you try to solve the whole problem, do you solve these different B's in parallel to see
Yeah.
optimize which B is the best?
Right, probably we need to do so. So the structure of the theorem is actually for simplicity of presentation. But when you actually solve this overall problem, you need to first think about, okay, what if I just choose to send from this packet, solve this whole thing, backend search, those things, low complexity, those things, and then come back to compare which position is a better position. And the problem is special enough such that always choosing from the same position is actually the best. When we find it as a special structure when we solve this problem. Yes, please.
I was just kind of related to this question,
Right.
but it's kind of different the way that you said you fixed B.
Mhm.
What if you have multiple parallel B's in the queues? What will happen? How will you choose the freshest data
Mhm.
when we have multiple queues? I mean,
Mhm. Right. So I mean, basically, if you have several packets that from the same source, and you can potentially send the several packets from the same sources simultaneously, I would say that probably you will be able to develop some policies that are near optimal, whether they are asymptotically optimal for the large system limit, like what has been happening for the Whittle's index. That part you probably need to redo all the proofs for Whittle's index, and could be optimal, could be not optimal. So in our model, we are saying that when we want to send from how do we say? I have multiple channels. I have a number of users, and I have a lot of packets in different queues, different buffers. So when I choose to send one user, the user give me the best packet from his buffer and send that. Okay. Now, if you think about that, okay, suppose that the transmission time is random, by considering sending multiple packets from the same source could be beneficial. Now, if the transmission time is constant, then there's no benefit of doing what you would say, like sending multiple packets from the same source, because they are delivered at the same time. You're just utilizing the channel resource. my answer that already mean this has fully addressed. You can still work on this.
Thanks for the interesting talk. I like your idea and method to study this problem. But there is one part in part one, I did not follow the Epsilon Markov model. So I'm just when we study the information theory, there is a notion called hidden Markov model. So I'm curious, is there any relation between your Epsilon Markov model and the hidden Markov model?
So Yin, you may want to repeat the questions because I just realized that for Zoom, they might not be able to hear.
I see. Let me repeat the question. So I have been utilizing this Epsilon Markov chain model, but this hidden Markov chain model has been used in a lot of these signal model studies. And what is the relationship between these two models? Well, we were motivated to find a model that can answer our question. And the hidden Markov model is motivated to find a model that fit the data in the best way. So the model that fit the data in the best way may not be directly help for me to answer the question that I want to answer. Yeah, so that is why we choose this particular model. And also we were actually motivated by this Professor Li Zhongzheng from MIT. He's working in the information theory area, and he has some tools to consider local information geometric. So we were introducing this Epsilon parameter because we are trying to look at, locally, how much your data is close to a Markov chain. Okay, and that give us these technical tools, but this Epsilon Markov chain model is not really existing in his work.
Thank you. So there was an idea that the packets that are arriving will be inevitably late because of the delay. So like the freshest packet is not that useful. The idea is coming from that fact that delay is inevitable, or if you assume the delay is zero, still that would hold true.
Yeah, I think you have a pretty good question. So your question is about that, stale packet could be useful. And what is the reason for that? Is that coming from the communication delay, or is that coming from some other reasons? So, so suppose that you have this kind of processing delay at the camera, or communication delay from the camera to your GPU. Okay, that will just keep you to have a scenario that you don't have fresh data. You can only have the data that is as best as fresh as age value. So that is the part, communication system and signal processing system limiting you to not have fresh data. Okay, but what we are observing here is that fresh data is not about availability of fresh data or not. It's about the question that is that fresh data more useful or stale data to be more useful. So we actually find that stale data is more useful in a scenario where you care about nearby devices' reaction to your movement. So if you're moving towards the left, and then the car on the left lane, they will somehow just move away to protect, to not have a collision with you. So that's the reaction we are trying to predict. So if you're trying to predict that, then basically you are trying to predict the other agents' reaction to you. And in that scenario, you find a little bit old packet is actually useful. Yeah.
Any other questions? Are there any online questions? Yeah. Looks like we should thank the speaker once again. Thank you for a very entertaining talk.
I know everyone is busy. Thank you for coming to my class.
And now we'll stop.